Mm. Should we start?
Yeah.
Okay. Okay, good afternoon and welcome. So because yesterday someone mentioned aerial vehicles, I decided to go through what I consider to be an interesting example on the cooperation between aerial and marine vehicles. We have not fully implemented the concept yet. So this is the work of a master student, Marcelo, together with myself and my colleague Rita. So what's the problem here? No, I have to come here. So suppose you have an oil spill, a chemical spill, or whatever. That's the thing in orange. And you want to find out what substances are there in the spill. And maybe there are people that advocate the use of they call it dispersants. So it's some substance you put in the water and sort of breaks the molecules of oil. So you have to send vehicles out there, marine vehicles, to actually follow the contour of the chemical spill and then do something about it. Other people even advocate the use of underwater marine vehicles to know the extent of the oil spill underwater. But the first thing you have to do is to detect it and track it and follow it. So the idea is to detect the oil spill from the air using a quadrotor, for example. So the top one sort of recognizes where the boundary is, does the detection online, and then follows the boundary, and it sends that information down to one or more vehicles that in turn go along the boundary, and then if they have to do anything, they will just do anything, like throw in some chemicals. So there are very interesting issues. This is a very practical issue, and there are other sub-problems here that are also interesting. So first of all, each vehicle must be endowed with good control systems to control along certain paths. You also need multiple vehicle coordination between the top vehicle and the surface vehicle, or surface vehicles, plural. And this is the case where the path is not defined a priori, so it's defined on the fly. So based on the vision, the quadrotor is going to acquire some point. It's going to fit some curve there. It could be splines, it could be Bezier curves or whatever. And then hands over this information to one or more marine vehicles that do the path following over a short time horizon. And then the information is renewed and keeps going. Okay, so it's very interesting because it brought together aerial and marine vehicles. So Marcelo did a very nice thesis. So there are some reference frames involved. I'm not going to get into the details. The autonomous surface vehicle, the motion is constrained to a 2D plane. And then, of course, I've covered the modeling, so there's no problem. And then you have the quadrotor that can, in principle, be modeled as a simple double integrator. Where the control inputs are accelerations, which are transformed into a set of desire, attitude, and thrust. So we have to follow a solution to find a solution to allow cooperative behavior between these different types of heterogeneous vehicles. So the first piece of the puzzle is path following, and this is something I have been talking about. So I think there's an animation here. So for the quadrotor, once it detects a path over a certain area, then it's supposed to follow this path, and then since this communicates information down to the surface vehicle, and the surface vehicle is required to follow this path as well. So there's a mathematical way of expressing this. I'm not terribly interested in this at this point. Essentially, you have to make the distance between the true position and the desired converge to 0. And also you want to do this at the desired speed. D stands for desire, okay? There are control laws that I will get into this at the later stage. My idea is to give you the main concepts that are involved, and then we'll get into this. So don't get distracted by the paraphernalia of equations. And then you have to synchronize the virtual targets, but here we fall in the realm cooperative motion control. I mean, you have the UAV quadrotor following a path that it detects online, the ASV converging to the same path, and they should somehow synchronize top to bottom. And this can be done by imparting on both vehicles a desired speed profile, and then you adjust according to how far they are from each other from the projections on the horizontal plane. And then I'll mention this. Okay. So there's a control architecture that goes with this, where you have the quadrotor, you have to execute a path following algorithm, and then you have to communicate with the, so this is a quadrotor. There may be more than one autonomous surface vehicle. They are all running path following algorithms, and they talk to each other, and then you run the cooperative path following algorithm. Okay, so for this, he created an artificial oil spill, not artificial, simulated an oil spill right there at the site where we usually carry out experiments. So that's what you have here. And this was created in Gazebo, which is a very good visualization package. There you go. So the problem is to start by detecting a boundary in the image. And then based on this information, then you should generate smooth reference paths for the vehicles to follow in real time. So of course, we are assuming that the boundary is located at the ocean surface, 2D plane. The quadrotor cannot see the entire environmental boundary, so it's exploring it as it goes about its life. And this means that out of the vision system, we can generate a planar point cloud of the boundary from the 2D image in real time. So the path planning, so at each instant, the quadrotor is following a desired path, and then it looks ahead and a certain point cloud is produced. You have to reject outliers, and then you start replanning at an arbitrary point in front of the drone. And then you keep doing this. The complicated part is when you get these points, you have to attribute some ordering to the points and discard the outliers. And then you replan and you keep going. Send to ASV, and you repeat and repeat and repeat. So I think Marcel will be able to explain this much better. So let's see what he has. Can you hear? Function and natural disasters to the human error. So we are having the echo again. Huh? Cleanup missions are usually very expensive to conduct. They require large vessels, specialized staff on board, and can also be very disruptive to the environment. But what if we do not make these tasks? Just a second. Okay. No. Natural disasters to the human error. Okay, hold on a second, please. Let's see if we can make it. Huh? Okay. Use a drone with a camera to detect the boundary of LARSyS.
then generate the path dynamically, and after that, we use an ASV to follow the path cooperatively with the drone. The ASVs can be used to stress chemical dispersants for use of functions in the water. This part has been the focus of previous projects such as Madras. But how do we achieve this? First, we create a control law that allows the marine vehicle to follow the originally ghost target or target that moves along the desired path. We test these algorithms using real user vehicles at Torpedo Lisbon. We then repeat the same process for the drone. The next step is to adapt the digital target of each vehicle dynamically. We should align with each other in order to keep the desired vehicle information. We then perform experiments to where two real user vehicles perform complex and for the third experiment, we can use a series of drone and a series of user vehicles on complex about four. Now, we have algorithms to follow path. What you see is to simulate another speed. For that, we create a 3D replica of Lockheed Solid Light with a red stain. We then put this visual world in video simulation. The next step is to take the output of the visual camera to a system that generates the path online on the boundary of the field. To achieve this, we take the image trace from the drone, segment the image, convert the white pixels to point clouds, and you bring the number to the points using graph search algorithms and point curve and send the path to the feed so that we can follow it. We repeat this process iteratively. For us, we are able to once you like this services.
Okay, so this is something that we want to bring up to a different level, because now there has been a combination of real experiments, but then simulations, but we actually wish to implement this because there's a high demand for these types of applications, which I find very interesting. So it involves the cooperation between aerial vehicles and marine vehicles. And of course, there are many, many other applications that involve the cooperation of other kinds of vehicles. It's interesting, for example, I was involved in the writing of a proposal to submit it to the European Union on cooperation between an aerial vehicle and a ground robot for some purposes. So the guy up there was supposed to look around, and then the ground robot would take it to specific spots. And the problem is the autonomy of the aerial robot. So it's very interesting because these days you can actually buy drones with umbilicals, and you can buy this system off the shelf. So you could go on a beach, if you are trying to clean that beach, then you sort of launch the quadrotor. It's connected via an umbilical to the ground vehicle. Then using vision can detect the spots where there's interesting stuff to pick up, and then you go there and do the job. And by having the umbilical, then of course you can keep feeding energy to the quadrotor, so you increase the autonomy. So there are many, many other applications out there. So I wanted to show this because yesterday someone mentioned something about quadrotors. Okay. So today we should go slow and easy because maybe some of you are already acquainted with this, others are not. So it's, for some of you, maybe it's something completely different, completely new. So we'll see what we can do. When you have a system that you wish to control, it could be a model of a ship, a quadrotor, a ground vehicle, so on and so forth. Then this is what essentially what we call a plant to be controlled, and you have a model. And the plant could be nonlinear. What does this mean? For example, remember that yesterday when I wrote down the model, there were terms that involve squares, things that have to drag and stuff like that. There were cross terms involving linear velocities and rotational velocities. So these are nonlinear models, okay? And they are considerably more difficult to control than linear models. So when we deal with control systems, oftentimes we use the letter U for the input. So in the case of the ship, it could be the propeller and the rudder deflection. And the Y could be anything, the position of the center of mass, orientation, whatever comes to mind. And this first slide is very generic. And I'm assuming that at least you learned something, maybe not too much, about linear control systems. There's this large dichotomy. Should we go for a linear control law? For example, the classical approach is to use what people call PID controllers. So you go to the output, compare with the reference, and you multiply that by a gain, proportional term. You compute the derivative and multiply by another gain, and you compute the integral and multiply by another gain. And there's a reason why we do this. But these are linear controllers. Why do we use linear control laws? Because there's a lot of engineering intuition to do this. Maybe you are not very much used to doing this, but when you have linear designs, then you can analyze systems in the frequency domain. For example, if you design a controller for a ship, velocity control, and you design a linear control and everything is linear, and you analyze the system from referencing speed to the actual speed, the system is linear. So this means that you can do what we call frequency analysis, which is you imagine that this system is attacked by different sinusoids, maybe with the same amplitude and different frequency, and you'll see how the system reacts. And by knowing how the system reacts to different frequencies, you learn a lot about the system. For example, you could say the system is going to respond well if my commands are up to 0.1 radian per second. That's what we call the bandwidth of the system. When I try to fit in references at higher frequency, then at the output, the response starts decay and the amplitude is less and less, and then you don't have good responses. So in electrical engineering, we call this the Bode diagrams. I think you guys use this in ocean engineering, maybe with a different name, but there's a very good physical intuition because it's the language of frequency. For example, when you have these systems and you bring in external disturbances, you could say the disturbances are concentrated over a certain region of frequencies. It makes a lot of sense. So the question is, how do I design a control law so that I may attenuate frequencies over that region of frequencies? So the frequency domain is very, very familiar to us engineers. And that's why I'm saying that there's very good engineering intuition. However, when you design a linear controller for a nonlinear plant, you have to assume that somehow you linearize the nonlinear plant. For example, if you have a ship going at steady state with a certain speed, and you look at the equations of motion, they are nonlinear, but you ask yourself, how can I rewrite the equations when I assume that the deviations from what we call trimming or steady state are very small? Then the model becomes linear, as I will remind you later. So everything is linear. The problem is when you go for a linearized version of the model, then you lose sight of what will happen if you deviate a lot. So there's a lack of global stability and performance results. That's the problem. And sometimes there's very poor physical intuition. So there's some engineering intuition in the sense that you can interpret using these frequency diagrams. But when you have a plant and you have masses and dampings and stuff in linearized, and suddenly you get the linear model, and it's an entity that probably doesn't bear much resemblance with the initial model. So that's what I mean by poor physical intuition. Okay. When you go for nonlinear control laws, you have extremely powerful stability analysis tools that give you guarantees even when you start far off from these equilibrium or trimming conditions. And possibly, and this may seem strange, there may be some very good physical insight. For example, if you have a spring, a mass, and a dashpot, and the thing is going to take too long to go down to equilibrium, and there are lots of oscillations, then what is your reasoning? Well, this means that the damping is not enough. How do I introduce a virtual damping? You know that damping is proportional to speed. So what you do is go to the position, you compute the derivative and inject back to introduce an artificial damping. That's what I mean by physical insight. The price that you pay is that you need a stronger theoretical background. And there are limited tools for performance analysis. So for stability, it's okay. For performance, it's slightly more complicated. So what's my preferred? When I look at the model and it's not terribly complex, and I get the feeling for what is going on in terms of damping and stuff like that, I kind of prefer nonlinear control laws. If you have a very complex system, then you better let the computer speak for itself. So you get a linearized model, and there are many tools to do the linearized control design. And then you have to be careful about making sure that when it deviates a lot, things will not go completely nuts. So let's start by talking a little bit about linearizations and control. And again, I'm not going to be very formal here, but I want to introduce these concepts. Suppose you have this vehicle, which is an underwater vehicle, okay? And you want to do something. So let's pay attention to the vehicle. So the body axis is there. So you have X and Y axis. And assume that the vehicle goes at a certain speed, V. V is the absolute value of the velocity, which is aligned with the x-axis. So I'm assuming that the so-called side slip angle is very small, and I'm going to neglect it. Of course, it's not true. When you go on turns, then you get some side slip. But let's forget about it for the time being. Now, there's another angle that we all know how to define, which is the adding angle between north and the velocity vector of the vehicle. So suppose you fix the speed, and I say the following: I want this vehicle, the center of mass, to converge to the path and gently move along the path. This is what we call path following, okay? So it's the first time I'm talking about it in a more formal way, but still without the mathematical machinery. So what you wish to do is set the speed of the AUV equal to a constant. And now choose the angle as a function of time so that the center of mass converges to the path, which means that what you have to do is to make the lateral distance that I called y converge to 0. If you make the lateral distance converge to 0, then the center of mass converges to the path, and you keep going nicely along the path. So let's think of a very naive way of doing this stuff. So the very first thing you have to do is to come up with what we call a plant model or a design model, which in this case is trivial, because if your velocity vector is here and this angle is psi, then by projecting onto this axis, you get the time derivative of y is v times the sine of psi. This is obvious, okay? So if psi is positive, this gives you a positive value and y will increase. If psi is negative, then it will start decreasing. So this is what we call a planned model, where the input is psi and the output is y. Now, you may wonder, oh, I don't see any dynamics here. I'm looking at the kinematics only. So the idea is, how can I compute psi? In other words, to decide on a control law for psi, such that the lateral distance goes down to 0. If I come up with a control law for psi, in other words, I'm specifying exactly what psi will do as a function of time. And if I can prove that the lateral distance goes to 0, then I'm done. Okay, then you have another problem because you have to control psi and to make the real psi follow the reference that you generate here. And we leave that for later. That's what we call an inner loop. So you have to design a controller for psi. So this is a trick that you use very much. If you don't want to make things too complicated, you start by designing at the kinematic level. That's what we are doing. So I'm going to design the controller for psi, and then later you kick in the inner loop design. So there's outer loop, inner loop, kinematics, dynamics. So remember that at a later stage, you have to bring in the controller for psi. So what's the objective of all these things? And in any control problem that you tackle, you should always be able to formulate in terms of deriving something to 0. Okay? So the objective is to reduce something to 0. What is it that you have to reduce to 0? The lateral deviation. So that's what you have there. So you start with a model. dy dt is equal to v sine of psi. It's a simple kinematic model. I mean, it's one of the most trivial things you can think about. Now, let's go along the path of linearization. If that angle is very small, because when the vehicle is on the path and goes north, the angle is 0. So let's assume that it starts off, but the deviation is not very big. That's a fundamental assumption for linearization. In this case, you know that if I write psi in radians, then psi and sine of psi are approximately the same. So you get the derivative of y is equal to v psi. Now the system is linear. That's what we call linearization. There's nothing magical about linearization. All you have to do is you start with a nonlinear model, and you go first for the equilibrium conditions. What are the equilibrium conditions? That's when the vehicle goes at steady state. So when psi is 0, then dy dt is equal to 0. So when psi is equal to 0, the derivative is 0. That's equilibrium. And then you perturb, but you perturb by small amounts. The sine of psi is confused with psi in radians, so that's the model. Now you have a trivial linear model. Okay, so now what can I do to bring y to 0? So here is the model. dy dt equal to v times psi. Remember, psi is the kind of stuff that you have to play this game. Now you have to come up with a control law for psi. And now use a trick that is very much used in controls, which is the following. This is what you have. You don't know what psi should be. But there's one thing that you know. You would like for y to go smoothly to 0, maybe exponentially. So you start dreaming of the differential equation that should be obeyed by the closed loop system, such that in closed loop, y goes to 0. So forget about these intermediate steps. If somehow, by a passive magic, you can choose psi, such that When you replace psi by whatever you decide, you obtain this equation, dy dt plus y equal to 0, you are done. Because the solution to this is an exponential, and you go to 0. So you have this, and you like to be there. And this is a very useful trick that you can generalize. Well, the way you do it is, in order to make this right-hand side equal to y, you simply make psi equal minus 1 over v times y. So if you substitute this in there, then the v cuts with the v, and you get dy dt is equal to minus y, and you are done. So it's a very simple trick that people use all the time. You have the real system, you want to achieve something. So remember that the first trick is to decide what is it that you wish to drive to 0. Why? If I want to drive it to 0 and I want it to satisfy a first order differential equation, then I might as well say that I would like for y of t to satisfy this differential equation. But you have this. So you choose psi so that you cancel, then suddenly you get this. This is very interesting because it essentially is telling you the following. If y is positive, then you divide by the speed, and then you give it this angle. If y negative, then you give it that angle, which is true because if y is positive, then the angle becomes negative. I mean, if you are here, you want to turn to the left. If you are here, you want to turn to the right. So you achieved success. It's a very, very simple example. It's a trivial example of a path following control system. Believe it or not, if you implement this on a boat that does not have much side slip, it will work very well. It's trivial. It's almost trivial. Okay. So how do you implement this now? Remember that you have the plant model. So your input is psi, and the output is y. So you divide by v, you feed back. You could even put a small k here, k. And then k would appear here, and then you would control the rate at which the y goes to 0. The faster the k, the larger the rate at which you go to 0. And boom, you are done. Okay? So now, of course, as I mentioned to you, all right, so okay, let's now go for a different thing. For some reasons, when you talk to guys that do fixed-wing aircraft control, they don't like to manipulate the heading angle. They like to manipulate the rate angle. There are many reasons why. Also, when you have a pilot, I have noticed this for small ships. When you have the pilot trying to follow a path, the pilot likes to control with the rudder the heading rate, not the angle itself. It's the rate. It's very interesting, in fact, because when you try to pilot one of these small boats and try to follow a line, if you look on the screen at the position of the boat and the line, and you start actuating the rudder, you'll go. But if you look at the bow of the small ship against the background and somehow get the feeling for the rate, angular rate, you'll be able to control it better. So maybe that's the reason why some people like to use rate control. So here I'm assuming that you are not going to control psi, but now you want to control this autonomous underwater vehicle through R, which is your rate. So in this case, you have this equation, but now decided is R, where R is the new input now. And then at a later stage, of course, you have to design a local controller for the vessel so that when you tell the vessel, go at this your rate, then the controller should be able to do that. So with respect to the model we had before, now this is a little bit more complicated, but not terribly more complicated, because you had the plant model number one, and you have an integrator here. So psi is the integral of R. So the question is, how do I specify a control law for R so that y is driven to 0. Again, it's a very simple case. So let's still do the linearization. So if I linearize, so this is the original model here, okay? So for small psi, actually y doesn't have to be small, but fine. Then what you get? You linearize this one and you get what we had before. dy dt is v psi, and the other one is already linear. Now you have two equations that are coupled. So you suspect when you put them together, you have a second order differential equation, which is true. I mean, if you compute the second derivative of y, so you have the derivative of this, which is v times the derivative of psi, which is r. So you get second derivative of y is equal to vr. Now this is your model. It's a second order model now, instead of being a first order model, okay? And again, the same question. How do you choose r such that y converges to 0, okay? And you do the same trick. Remember what we did before. You had this first order differential equation. You want the y to come to 0. If you don't have any idea of how to choose psi, be pragmatic and say, this is a first order system. If the closed loop satisfies this linear equation here, then I have exponential convergence to the origin. So this is what you had in mind. And then this gave you the hint that psi should be like that. Now you have the same problem. You have a second order differential equation where the input is r. How are you going to choose r such that y is going to 0? Okay. In a general second order differential equation, you have the second derivative, first derivative, independent term, and then the input. And here everything is missing. You don't have the first derivative, you don't have the independent term. So put them inside, okay? So this is what you'd like to have at the end. Second derivative plus some gain times the derivative plus k1 times y equal to 0. If the k1 and k2, there's a fundamental result in stability theory that says if you have a second order systems and all the coefficients have the same sign, then the system is stable. So if you choose k1 positive, k2 positive, you'll have a solution that goes down to 0. So again, this is your dream. This is your dream differential equation, but this is what you have. So what should I do? Well, you do the same trick. You play the magic and choose an r such that when you insert it in here, boom, the equation becomes this. So obviously what you have to do is to make r minus 1 over v times k1. So the v cuts with the v and you get k1. And then plus k2 derivative. It shows up there. So when you do this trick and choose the rate of turn in this manner, now you have convergence to the origin and you bring the lateral distance to 0. Look at the control law. It makes a lot of sense. And that's what the pilot actually is doing to some extent. So the pilot looks at the distance from the path, looks at the rate at which this thing is changing, and then imparts a certain yaw rate by controlling the rudder. So in fact, what you have here is a PD controller. So it's a proportional and a derivative control law that you have there. See? So it's nice and easy if you go through these linearizations. Okay. How do you implement this? So you have the plant model. Your input is R. Again, let me remind you that R in the kinematic equations is considered as an input. But if you were to implement this controller, then at a later stage you'd have to design a control system for R to make the vessel actually go at that heading rate. So you have the plant model, you have Y, you measure with GPS, you do an approximate derivative of the GPS signal, and you can put dy dt. You do this feedback, and this works like a shark. So you are having feedback from the lateral error and the corresponding rate, and it's a great control law. It's physically based, you see. Now, in practice, what is lacking here? Well, you see, here you have R, but now you have to control R. So when you give it the desired R in there, then you go to the inner dynamics of the system. You actually measure the actual R, compare with the desired R, and you have to design a controller that will impart a torque based on the deflection of the rudder that will generate that R. So that's the complete system for path following. And of course, it's the simplest one I can come up with, okay? And this gives you an idea of how we use linearizations to this control systems design. Okay, let me give you another example of control design where I touch a little bit very lightly on cooperative motion control. So suppose you have a car that moves along the coordinate Z1, sorry, and then you have a quadrotor that moves along a coordinate Z2. And the velocity of the car is fixed. It's V1 equal to V star. It's fixed. And the quadrotor knows that. So you launch the quadrotor, and you want to derive a control law for the quadrotor, adjusting its speed V2, so that the quadrotor, when time increases, will be exactly on top of the car and follow the car at the velocity V star. Okay? Again, to do this, you have to look for the variable that you wish to drive to 0. But this is obvious because if you look at Z2 minus Z1, so Z2 is the distance traversed by the quadrotor along this line, and Z1 is the same for the car. So for example, if this guy is ahead, you have an error, which is Z2 minus Z1. But it could be to the other side, of course. But it doesn't matter, because what you wish to do is the following. Choose the speed of the quadrotor, V2, so that E goes to 0. That's your control problem. So again, you have selected the variables that you can manipulate. And also you have selected what variable you should bring to 0. These are the key ingredients in the formulation of a control problem, right? Okay, this is essentially what I told you. So let's do this. If you want to drive the error to 0, you have to write down the dynamics of the error. So remember that error is Z2 minus Z1. So if you compute the derivative, you get derivative of Z2 minus derivative of Z1. But the derivative of Z2 is what we call V2. It's the speed of the top quadrotor that you wish to control. And then you have the speed of the bottom vehicle that is fixed. We can extend this to the case where it is not fixed, but let's start this way. So you see, you have the plant model in which the inputs are V star and V2 minus V star, and then the plant model is simply an integrator. This is an integrator. So again, I remind you, you have all the ingredients that are required to do this. So you have identified the variable that you wish to drive to 0, and you have identified the variable that you can manipulate, which is V2. Okay, so when you write down the equations, you get this. dE dt is equal to V2 minus V star. And the question is, what should V2 be? And you do the same magic trick. This is a first order differential equation. May look a bit weird, but what would you like to have? You'd like to have the error converging to 0 exponentially. So you say, well, I'm going to do some magic here, and then I would like to obtain dE dt equal to minus ke of t, because then you know that the solution to this thing is an exponential with the rate of decay that is related to k. So it's obvious that what you have to do is to make V2 equal to V star, that kills that one. And so you kill what you don't want and introduce what you wish to introduce. So if you make V2 equal to this V star cancels that one, and you get this beautiful differential equation, and the error goes to 0. Okay? And what this tells you is very simple. It simply tells you that if the quadrotor knows that the ground vehicle is going at the speed V star that is fixed, okay, there is not much that the quadrotor can do at the beginning. So, okay, let me go at V star, the same speed. But now I'm far ahead. Okay, I compute the error. The error is positive, so I slow down, or vice versa. If it is behind the ground robot, I speed up, and that's it. So it's a very, very simple form of cooperation, but you see the main ingredients of a cooperative control law. In any cooperative control law, all the robots will be driven by what we call a nominal speed, and then you have the correction term that has to do with a mismatch between the positions of the robot. So all the key ingredients are here, okay? Now, there's a problem here because the quadrotor will have to know what V star is. So if these two vehicles are truly cooperating and they are friendly to each other, okay, they share the V star. But suppose you have something down there and you don't know the speed. Is it possible to achieve cooperation without knowing that speed? So that's an interesting question. Okay, first this is the implementation, right? So there you go. Okay, so decrease the speed when R2 is ahead of R1 and increase when it's behind. So we know this. Let's go now for the dynamics. And there's a reason why I'm going to do this. So if you have the dynamics, the equation for the error is still the same. The derivative of the error, it's the speed of the quadrotor minus the speed of ground vehicle. But now I'm going to say that the quadrotor achieves a certain speed by manipulating the force along the x-axis. And I'm going to use a very simple model, no drag. Force is equal to mass times acceleration. Okay, it's closer to reality. I'm already getting closer to the inner loop. So of course, if you do this, then you reach the conclusion that F is d square E dt2, okay? Because if you do dv2 dt, here you get square, the derivative of 0, this is what you get. This is what we call a double integrator. So the error will be the double integral of the force that you apply. So you have another plant model where now the input is the force and the output is the error. And again, now the question is, how do I select the force that I have to apply to the quadrotor using the propellers so that that error goes down to 0? Okay, so that's the model that you have there. And now user-centric. This is the error. And you have a second derivative and you have F and you have no idea what the F should be. Well, You want the error to go to 0, and the error will satisfy a second order differential equation. Again, if you can do some magic and introduce the f such that the equation becomes second derivative plus, oops, this should be e, plus first derivative plus error equal to 0, and all these coefficients are positive, we know that the system is stable and the error will go to 0. You see, it's the same trick again. So how do you go from here to there? Well, you simply do f equal minus k1e minus k2 derivative. So if you put this in there, you get this equation. And this is very interesting because what you are doing is what we call proportional and derivative control. You look at the error and you feed the force, and you look at the derivative and you feed into the force. So it's a very simple control law, all right? Now notice the following. You don't need to know V2 star. It should be d dt. Yes, I know that. Thank you very much. Thank you. Okay. It does not need to know the V star. So all that you need to know is that the ground robot will move at a constant speed and the system will learn. V star vanished out of the picture. There's a reason why this is so, but it comes out of the equations, of course. So how do you implement this? So you have the quadrotor, doesn't have to know the V2 star or the V star, measures the E, measures the rate of variation of the E, feedbacks the derivative, feedbacks the E. I should try and get rid of this. Oh. Okay. And boom, the thing works. Okay. So these are very simple examples of control laws that are essentially linear, but sometimes they are extremely useful, very useful. It's interesting that you can extend this to the case where you tell both the robot on the ground and the aerial vehicle, hey, gentlemen, I want the two of you to go at V star, so go about your life. So it may very well be that the ground robot will have some difficulty in achieving V star. In this case, how is that guy going to react so that it will be on top? And I'll talk about that later. But for the time being, this is very easy. Okay. Okay, and then you can complicate this a little bit if you have the system with RAG, because you have the error Z2 minus Z1. d dt is V2 minus V star. So the second derivative of this, we have seen this stuff. Now, there's something missing here. Yeah. So the EDT is V2 minus V star. But now I'm going to introduce drag. So the force is not simply d do dt2, but it has a drag term. Okay. So what happens now? This force is equal to beta, and V2 is going to be a value around V star. So V2 is V star plus d dt. Okay, because the dt is dv2 dt, and then you have this other term over there. So again, determine f such that in the limit the error goes down to 0. So this is the first time that I'm going to do something along the lines of linearization techniques. I have done it for the sine, but if the force is equal to beta v star plus derivative squared, this is a nonlinear term. This is a nonlinear term. Okay. When you want to linearize something, the first thing you have to do is to find what we call the equilibrium condition. And what is the equilibrium condition? That's when everything is stopped. That's when the error is 0 and the derivative is 0. If this is the case, right, then you have f star is equal to beta v star square, which makes sense. If you are at steady state and you are going at a certain speed, then the force has to counteract the drag term. I'm okay. Okay, thank you. So that's the equilibrium condition. When you are flying nicely at V star, you apply the force that compensates for the drag. But now the system is going to be disturbed. So maybe you will need to apply a certain variation around F star. So you put here F star plus delta F, and now you perturb this term as well. It's going to be V star plus something. So you bring it here. And then you have the D2, so you are here, right? So when you do the square of this, and then you get the cross term and so on and so forth. Oops. So now notice the following. At equilibrium, F star is equal to the drag force, so these cancel. And now you are going to neglect the higher order terms. So all terms that are square, you cut, and even higher order terms. So this means that you are dealing, with a very simple system, which is delta F is equal to dE dt, so plus d2e dt2. So it's a second order linear system now that tells you how the error is going to evolve by manipulating variations of the force about the trimming condition. I'll repeat this with an example, with another example. So then you design another controller with rate feedback and variable feedback, and you can achieve stability of the system. All right. Let's do this more carefully, because that may have confused you a little bit. So let's do another example. Suppose you want to control a torpedo underwater or a submarine. So you start by writing down the equations. And what are they? The sum of all forces, so it's moving only in one direction. The sum of all forces is equal to the total mass, which is mass plus added masses, times the acceleration. So what other forces are involved there? You have a linear drag force and a quadratic drag force. Okay, so this is the model. It's a very simple model. So the sum of all forces is equal to the total mass times acceleration. So the input is the thrust provided by the propeller, and the output is the V, and you are trying to control the V. You wish to control the V, the speed of that torpedo. So normally we don't have this linear term, but for the vehicles that move very slowly, they end up appearing there. So I put the linear term. Okay. So suppose I want to do something that is a bit more sophisticated. So in practice, sometimes people design controllers for fixed speeds. I want my torpedo to go at 3 knots, 4 knots, 5 knots. It's fixed. I may be interested in having the speed track a certain reference. It goes 1 knot, 0.5, 0.2, and then so that's the reference for the speed. That's the reference I wrote down there. So how do I formulate the control problem? Generate the thrust such that when time grows, the true V will converge to the reference V. So reference is desired, V is the true value, V is the true value of speed. How do you formulate this problem? Again, you have to look for the variable that you wish to drive to 0. So the error is exactly what you have there. V reference minus V. This is what you want to drive to 0 by manipulating the thrust. Again, a control problem that is very well formulated. So if you want to drive the error to 0, you better find out the dynamics of E. What's the differential equation that E is going to satisfy? All right, so you multiply this by mt, and then you compute the derivative. dE dt is equal to something dvr dt, and then dv dt. Okay. Now, because you know VR, because this is the speed that you wish to track, it's stored on a computer, you know the speed as well. So in fact, you know dvr dt in advance. Okay, so what are the error dynamics? Very simple. So forget about the MT, let's assume it's 1. dE dt is equal to dvr dt minus dv dt, and dvr dt is known. So everything boils down to finding the t such that the error will come down to 0. It's not clear how we are going to do this, but let's start expanding this. So mt dE dt, there's nothing you can do about that. mr dvr dt, you know that. And now notice that here I have dv dt. So I go back to the model, and you have dv dt here. So you divide by mt, you get t minus beta v minus fv squared. So that's what you'll end up with there. Okay. So now we have a big mess because we want to drive the error to 0. This is the thrust that you want to generate. Fine, you know VR, but you have V and V. So what is it that we can do? You do the same trick. So you would like for the error to satisfy a nice differential equation such that you look at it, well, the solution is going to 0, right? So that's exactly the same trick. So how do you do this? Pay attention to this. You are going to select this thrust in such a way that you cancel this term because you don't like it, and truck, and you cancel that term, you cancel it. You cancel that term. So essentially you cancel almost everything. And then you introduce the term K times E. And when you replace this on top, then it gives you this horrendous thing. So you get mt dE dt, mt dvr dt. Now you stick the t in there, beta v fv squared, and suddenly all these things cross. And you have a first order differential equation that goes down to 0 because it's exponentially decaying. Okay, beautiful. So this means that you have, if you have a VR that you want to track, all that you have to do is to implement a control law whereby the thrust is given by the derivative that you know. It's also proportional to the error between the true speed and the desired speed. And you also sort of feedback the true velocity. And this works. So it's a bit amazing because, in fact, the reference is even time varying, but you shall be able to do it in a very simple manner. Okay. there you go. Look at the control law. It's a bit more complicated, but you can still implement this. And the tracking error goes down to 0 exponentially fast. So simple and elegant. So where's the caveat? There's a huge problem with this. Because when you implement this control law, you are swearing that you know exactly the beta and the F in your true system, right? Because you start with a model. And you are swearing you know exactly these two guys, such that by making t equal to this, you cancel those terms. And that's what can get you into trouble. Because if you make a big mistake in the identification of beta and F, it may very well be that you think you will be doing well, but in fact the system will go unstable because you are not canceling those terms, and then you don't know if the system will be stable or unstable. You don't know. Too bad. It's a beautiful idea. You use simple concepts and you deal with robustness. Oh, okay. So you use simple concepts. In robotics, when you want to do manipulation and stuff, this method used very much because people go through the trouble of finding the parameters with good accuracy. It's called the computed torque method. Sometimes people call it exact linearization. Why exact linearization? Because you started with something linear, non-linear, and suddenly you get a linear system at the end without doing approximations. I did not do any linearization. I canceled non-linear terms, so that's called exact linearization. So it's too bad. The idea is good, and if you know the parameters of the system with very good accuracy, you'll still be able to implement this. If you don't, then you cannot do this. It used to be in old times, in the old times, 60s and stuff like that, when people were trying to control spacecraft. And still they didn't have those appendages and stuff like that, the solar panels, so on and so forth. The parameters were known with very, very good accuracy. So you could use control systems like this. But the moment you start having some uncertainty in the parameters, then you have a problem because you think you are doing good, but then you end up not canceling exactly, and you don't know in which way the system is going. Could be stable or unstable. But this gives you some hope that probably when you have to control a nonlinear system, maybe there's some hope about finding a method that is not horrendous, because like this one is so elegant. Okay, it has this problem, but maybe there's some hope that there will be another way of tackling these kind of control problems. All right, so this brings us to Lyapunov theory of stability, which is something that was completely revolutionary at the time. It has more than 100 years now, but it was a big revolution. As you'll see, the idea in insight, the idea is, oh my God, that's trivial. Yeah, but trivial ideas are the product of geniuses. Okay, and Lyapunov was a genius. And he simply had a different way of looking at things. So let's find out, for those of you that are not familiar with Lyapunov theory of stability, what this is about. So let me give you a very simple example where you have a free mass subjected to a simple oh, that sentence is not okay. So all I'm saying is that I have a ball, a mass. It's going at velocity v, and it has some resisting force that is proportional to v. So I'm not thinking of anything physical, because normally it should be v squared. Okay, so the sum of all forces, which is minus fv, is equal to mass times acceleration. So if you imagine this in an hypothetical fluid where drag would be linear, Your intuition tells you that if you start with a certain initial speed and you let it go, the thing will decay because there's dissipation of energy, so on and so forth. That is obvious from the equation, because if you compute the derivative of v, and then you put this guy on the right side, you get minus f over mv, and this is very important. Now you can actually compute the solution to the differential equation. So v is equal to the initial velocity, and then there's an exponential decay. So what you do is you have this thing going down to zero. So no big deal. Why am I talking about this? Remember what you had to do to convince yourself that the velocity will go to zero, or the speed. You solved the equation. You solved the equation. If you have a very complex system, perhaps you'll not be able to solve the equation. And the question is, how can I still guarantee that the variable that I'm interested in will go to zero? That's where Lyapunov comes in. And again, please pay attention, because the concepts are very simple. I would say almost naive, but in a genial manner. And it changed the life of people completely, at least those doing controls. So then you can show that if V is positive, V is negative, they will go to zero. So no problem about that. Okay. All right. So there's some lingo here that people are starting to use. When you have a differential equation, you call an equilibrium point. That's the point at which nothing moves. So if you make V equal to zero, nothing moves. That's an equilibrium point. So that's the point at which the derivative is zero. And what you have shown here is that the trajectories converge to the equilibrium point. So the solution V equal to zero is what we call attractive. Okay. All right. Now comes the big question. How can we prove that the trajectories go to the equilibrium point zero without solving the differential equation? How can this possibly be done? So I think I'll stop here for our recess, because I don't want to get interrupted when I go through this, which is the fundamental idea. So we'll stop, I don't know, 10 minutes or so, and then I'll come back and I'll resume this, okay? Okay, so we'll have a short recess of 10 minutes or so. Okay. Coffee and monkeys. Not many? Okay, so it's good.
There were some people waiting. They were not giving access, so you can also. There were 2, 3.
Oh, because they told me that they would give access. Or should they already there?
No, they were.
No. Oh. Okay. Well, where is that? Oh, that's too bad. I didn't see. I didn't see. I switched off. No. Super. Okay, can we start? Okay, welcome back. So, summing up, you could show very easily, the intuition tells you that the speed should go to 0, but solving the differential equation, it's obvious because you have some exponential decay. So Lyapunov asked himself the question in the case of complicated differential equations, is there any hope of showing that the equations, the solutions get down to 0 without solving? The animation is not in the right order. So here is the fundamental idea. I'm going to look at the energy of the system, which in this case, it's very easy. It's only kinetic energy, 1/2 of m times v squared. That's what he called an energy function. So forget about the trajectories. I'm looking only at the energy. Okay. So in this case, we have v. We don't know how it is going to evolve. But for each particular v, we have a corresponding energy that is given, and then you have this energy function. Notice that this energy function satisfies a certain number of conditions. It's always positive, except at the origin. And in fact, it's only 0 at the origin. Okay. People call these functions positive definite functions, positive definite. And now he posed the following question. Without looking at the trajectories, maybe if I look at the energy and can show that the energy is always, this is the fundamental part. If I can show that the energy is always decreasing somehow, it's still a mystery of how one could do that. Then if I can show that the energy is always decreasing, then if I have something that is always decreasing and is lower bounded by 0, then the energy goes to 0. And the energy can only be 0 when the speed is equal to 0. So now you may say, well, you know, instead of writing down the solution to the differential equation, now you invent this problem of looking at the energy and showing that the energy is decreasing. How should we do that? So look at the animation. If you can show that the energy is always decreasing, right? Then it goes to the origin, and this means that the V does something you are not interested in knowing exactly, but goes to the origin. Now, here is the beautiful part of it. It's very easy to show that the energy is always decreasing. And look at the simplicity. You have sometimes this is called a Lyapunov function. So it's like a parabola. That's the energy. And now you ask the question, along the trajectories of the system, which I don't know, whatever they are, can I show that the derivative of the Lyapunov is always negative? And this is how this is done. So you compute the derivative of this with respect to time. So the derivative of this with respect to time, you have the composition of two functions, from t to v and from v to capital V. So you start by computing the partial of capital V with respect to small v along the trajectories, but you don't know them. And then you compute dv dt. Now here is the magic. If you do dv dv, what you get 2mv that you cancel with that. So you get mv along the trajectories. And then you get dv dt. Okay. But where was this now? dv dt. Well, this is not. Oh man. But remember that dv dt is minus f over m times v. So when you replace there, when you multiply this by dv dt, you get minus fv squared. F is positive. No matter what v is doing, v squared is always positive, and therefore this is negative, and the derivative of the Lyapunov function is negative, and you are done. So notice through this very simple example, the strategy. The first thing is I have to concoct. Sometimes people, when we try to solve a problem and we don't know if it will work or not, we invent some energy function. At this point, it's a candidate Lyapunov function. The first thing is the Lyapunov function always an energy function? No. If you are dealing with chemical process or population dynamics, then maybe there's nothing to do with energy. But you seek inspiration from mechanical systems. And then building candidate Lyapunov functions can be an art. Okay, so you have to read a lot of papers, seek inspiration, get to know what Lyapunov function candidates work here and there, and then you have this menu of possible Lyapunov functions, and then at some point maybe you'll have to invent one. So that's the first thing you have to do. You have to invent a candidate Lyapunov function, which in this case is trivial because it's the kinetic energy of the system. And now how do you compute? So let's do it again because it's very important. How do you compute the derivative with respect to time? It has two terms. The partial with respect to v. You don't have to do anything because the partial with respect to v is mv. It's mv, nothing complicated. And then you have dv dt. Well, but dv dt is what you started with. It's the dynamics of your system. So without doing many computations, you simply were led to the conclusion that the time derivative of the candidate Lyapunov function is less than 0. Here you declare victory and haha, this is a true Lyapunov function. And you can show, I mean, there are results that will tell you that in this case, the trajectories, and you don't care about them, they will converge to the origin. So we are saying that the origin is a stability point that is attractive. All the trajectories go down to 0. This is fantastic because, again, as I mentioned to you, you don't have to solve the differential equation. Are there any questions? Because this is the crucial step. If you are confused about this, let me know right away because it's very, very important to understand this. As I mentioned, it's trivial. In hindsight, it's almost naive, but it's a fundamental idea here. This was introduced by Lyapunov. So you don't look at the evolution of the trajectories, but you look at the evolution of the energy. And you can find out that the energy is always decreasing by doing trivial computations. You don't have to solve any differential equation. Okay. So now, if you have a function that is bounded below by 0, and it as always, the derivative is always negative, then the function has to converge to 0. And if the function v converges to 0, and because it's only 0 and the speed is 0, the speed will go to 0. Now you may say, okay, so that only shows that the speed is going to 0, but is it going to do some wild maneuvers? At this point, you are not interested. You just want to stabilize. In this case, you don't even stabilize. It's the system naturally goes to 0. All right. So beautiful. There you go. Okay. Now, suppose you have a more complicated case in 2 dimensions. I don't know if you got, yeah.
Yeah, that's showing that it cannot go below 0, right? Rather than showing that definitely it will go to 0.
Because if you have a positive function that is bounded below by 0, and the derivative is always negative, you have to go to 0. Okay? That's it. There's no way. There's no way. It does not get stuck at some point, because otherwise the derivative would be 0 at that point. Okay. I don't know if you guys, something happened here. Oh no, okay. If you guys are used to the state space formulation or not at this point, I don't know. Huh?
Not any of them.
Okay, for example, if you have a second order system where you have second derivative plus k1 times first plus derivative plus k2 times the variable itself equal to 0, instead of writing a second order equation, you may write in terms of 2 first order equations. It's a trick that is normally done. But anyway, yes, please ask the question. So chat. Is it possible to choose Lyapunov candidates which are not from the system dynamics? I think it's not clear what you mean. Okay, a Lyapunov function, finding one is an art. Because in very simple mechanical cases and electromechanical cases, most of the times it's simply the total energy of the system. But if you are dealing, like I said, for example, with population dynamics or reactions inside the reactor, and you look at balances of mass and concentrations of variables, maybe the energy does not mean much. So if you are trying to decide whether the reactor is stable or not, and you would like to show that the trajectories of some variables go to 0, and if you go along these lines of Lyapunov stability theory, you don't have the energy. So typically what you do is the following. Even when you have a complicated or a complex differential equation, it helps you a lot if you try to seek a mechanical equivalent. For example, if you have a phenomenon, like I said, evolution of the population dynamics of species, and the density or the concentration of population is given by second order differential equation. Second derivative, first derivative, independent term. You can find exactly the same differential equation when you study the system that is the mass, the spring, and the dash pot. And you know how to write the energy for this system. So you violate your intuition and says, well, I know how to write the energy for the analog mechanical system. So let me go along and invent something that is not a true energy, but that may work. So that's how you approach it. So when you are saying that choose Lyapunov candidates not from the system dynamics, yes, most of the times they have nothing to do with whatever you are trying to analyze, because what you do is you do some form of analogy with a mechanical system, and that will inspire you to write down a candidate Lyapunov function. That's how it works. Okay. Did I answer your question? Maybe not. Okay, welcome. So suppose you have a system that consists of 2 variables. The derivative of the first variable is equal to the second one minus k1. Now, when I write k1 x1, I don't mean that this is k1 times x1. K1 is a function of x1. So right here you have a non-linearity. When I write derivative of x2 minus x1 minus a function of x2. When you look at the system like this, the first thing you ask is, what's the equilibrium point? So the equilibrium point is the set of variables at which the system stops. So if this function is 0 at the origin, And this function is 0 at the origin. When you make x1 equal to 0, x2 equal to 0, this is 0 and the system stops. That's the equilibrium point. So 0, 0 is the equilibrium point. And now we ask the question, if you start off the origin, will the trajectories converge to the origin? And my God, how are we going to do this? We don't know how to solve this equation, especially because you don't even know the shape of this function here. All that you know two things to simplify it. You know that at 0, the functions are 0, and the functions are in the fourth and the first and third quadrants. So they go like this. That's all you know. Whoops. So normally, and I'll go slowly now because some of you may not be familiar with this, when you have a system of equations and you stack the x1 on top of x2, you call it the state vector x. And then you can always write these two systems, these two equations as a simple big equation, dx dt equal to f of x, where f of x is a vector of functions. This is a very common thing to do. It's very useful, okay? It's just a method of notation. So is there any hope in showing that the trajectories will converge to the origin? Okay, invent a Lyapunov function or candidate. I have no idea. I mean, this could be from some physical, chemical, energy-related system. I don't know. Okay, but let me try. I could think of extending the concept of the paraboloid, of the parabola, to a paraboloid. Will it work? I don't know. So I simply do this. 1/2 of x1 squared plus x2 squared, and now you get the paraboloid. Okay. Notice again that this paraboloid satisfies the conditions of a candidate Lyapunov function. It's a positive function, except it's always greater than 0, except at the origin. And x1 squared plus x2 squared is a very particular case of what we call positive definite forms. I mean, you may remember from your times of analysis something that when you write what we call a quadratic form, x transpose qx with q positive definite matrix, then it satisfies these conditions. But let's not complicate things. What I'm saying is that here q is identity, but you may have to go to more complicated cases, but that's fine. So what do you hope to establish? You don't look at the trajectories, it's always the same. If you could show that the energy is always decreasing, it's not energy, let's call it energy. If you can show somehow that this is always decreasing, and because it's bounded below by 0, you go to 0. And because the function is only 0 at the origin, x1 and x2 go to 0. Beautiful. And again, you don't even know what these functions look like, k1 and k2. So another question is, how do you do that? In exactly the same way. So here, I'm assuming that these functions satisfy this. x1 times the function is positive. This means that the function is in the first and third quadrants. Okay, it's physically. And the same for k of x2. And this is the candidate Lyapunov function. So as I mentioned to you, these two equations can be written in vector form as dx dt f of x, where x is a vector. And f of x has two components, one component, second component. Now, if you try to show that the derivative along time of this capital V is negative, you have to think of how you construct the Lyapunov function. So time is flowing. As time flies, the x that sometimes we call the state is doing something that you don't care about it. And once you compute x of t, you compute the value of the candidate Lyapunov function. So you have a composition of functions from t to x and from x to v of x of t. So how do you show that dv dt is less than 0? You do exactly the same steps. You do the partial of v with respect to x, and then you compute the derivative of x with respect to time. It's slightly more complicated because this is a scalar, this is a vector, and this is a scalar. So scalar, vector, and scalar. So how do you do the partials? dvx dt is the partial of v with respect to x. And because v is a scalar and x has two components, this is called the gradient of the function. It's a 1/2 matrix. So you have dv dx1, dv dx2. And then you have dx dt, which is a 2/1 vector. So it's okay. 1/2, 2/1, you cross, you get the 1, 1. So you have to compute this. So now let's compute it. So dvx dt is equal to dv dx. This is the gradient of the function. So the first term is the partial with respect to x1, which is x1. The second is the partial with respect to 2, which is x2. And then you have to go for the x dt. But the x dt is this function here. So you stick it in there. Boom, boom. That's the derivative with respect to time of the candidate Lyapunov function. Now you do these computations and you get x1, x2 minus x1, k1, x1, x2, x1 negative sign, and x2, kx2. So this guy kills that one. And because I have assumed that these functions are in the first and third quadrants, x1, kx1 is positive, x2, kx2 is positive. So these two cancel. This is positive, positive, negative. The derivative is negative. So you know that no matter what the system does, and without solving the equation, the differential equations, the trajectories will go to 0. It's a very powerful result. And this is just a simple example. Okay, so that's the strategy. That's how we use Lyapunov theory to show that the trajectories converge to an equilibrium point, which in this case is 0. Okay. Yeah. A row vector. Because, yeah, it's a matter of notation. Because most people, when they compute dv dx, they put dv1, dv dx1, dv dx2, and then they transpose to become a row vector. But if dvx for you is immediately a row vector, then you don't have to put the transpose. Did you understand what I? That's why it's up to you. You need a vector with two components, partial with respect to x1, partial with respect to x2. If you use it as a row or a column vector, it doesn't matter. In this case, I'm using as a column vector, and that's why I transposed it. Okay. So in other words, you could say that the derivative with respect to time of v is the inner product of the gradient times the vector field fx. Then it becomes clear. It's the inner product. So you have to do this and this. Okay. Notice that many times people talk about examining the convergence of the trajectories to 0. Why 0? I mean, maybe they converge to some other point. So again, when you open books on Lyapunov control theory, people are very much focused on ensuring that the trajectories go to zero. It doesn't have to be that way. So shifting. Is the origin always the true origin? And the answer is no. But through a coordinate transformation, you can always make the origin the equilibrium point. So let's study this very simple system: the mass, the spring, and the dashpot. So the sum of all forces is equal to mass times acceleration in the vertical. What are the forces? Gravity, that pulls you down. Then you have friction in the damper, that is a function. You see, I'm writing it as a function of the derivative. I'm not assuming a linear model. All that I'm saying is that this is a function of the derivative. At zero, it is zero, and it goes through the first and third quadrants. And the same for the spring. The spring is not a linear spring. It's not an elastic spring. So it could be a function of y, but it goes through the origin, and it's in the first and third quadrant. So that's the model. What's the equilibrium? Well, it's obvious the equilibrium is reached when y is equal to zero, right? Sorry, when the derivatives are equal to zero, everything stops. So if everything stops, this is zero, and you get mg is equal to k times the y, that is the y of equilibrium, which is obvious. I mean, you have a system like this, you let it bounce and die, it goes down and stays there. So it goes to a point where the restoring force due to the spring compensates the pull of gravity. All right. Okay. So here is a situation where the equilibrium point is not zero. In fact, the equilibrium point that consists of position and velocity is y equilibrium and zero. So if you go, if you write this in the form of a differential equation, you get the vector consists of y and dy, because you have a second order equation. So you can strip it down and convert it into two. So there's y and dy. The equilibrium point is y is something, and the derivative is zero. And then you can write these equations, as I mentioned before for the other case, by stacking y on top of dy dt as a big vector dx dt. And the right-hand side, you call it the big capital of fx, and of course, f of x equilibrium is equal to zero, right? So let's see if y of equilibrium is attractive, which is obvious from a physical standpoint. When you pull it and it will go back to that point. But let's show, even with nonlinear springs and dampers and stuff like that. Okay. So in order to study this, you have to ask the question, suppose I'm at equilibrium. Equilibrium is y equilibrium, and the derivative is zero. And now I perturb. Will I come back to the equilibrium point? So how do you perturb? You say x is equal to x of equilibrium plus some variable. It's just a shift of variables, change of variables. So psi is the difference between x and x equilibrium. I'm not doing this for small perturbations. I mean, the psi could be quite large. So then when I do dx dt, I get dx of equilibrium dt, which is zero, because x equilibrium is a constant, plus d psi dt. So in fact, instead of studying x, you are now going to study psi. And it so happens that d psi dt is the same as dx dt. Okay. Now, if dx dt is dx dt, because dx dt is equal to f of x, And x of equilibrium mass plus psi. This is equal to f of x of equilibrium plus psi. This is a function of psi only because the x of equilibrium is well known. So you call this function g of psi, this function. And now notice the very interesting thing. G of 0 is f of x equilibrium plus 0, so it's f of x equilibrium. But f of x equilibrium is 0. So you have recast the differential equation, the big differential equation. Instead of writing in terms of x, you write in terms of psi. It satisfies this equation. This side is equal to g of psi, and g of 0 is 0. The origin is now the equilibrium point. So by doing a simple coordinate transformation, you convert the problem of studying whether trajectories converge to the equilibrium point or not. Instead, you study the convergence to the origin. It's a very simple trick. And the what? No. Let me go here. Yeah, let's be careful about that. Okay. Suppose you have these two equations, right? Okay. And you have two. You could have 3, 4, 5, 6, 7, 8. Instead of writing them down, people like to stack the variables one on top of each other. So for example, x1 and x2, you call x, right? Yeah, it's a function on the right. It's a function on the right. Yeah. Okay. I'll skip now these slides. They will be there if you wish, but it's not terribly important. So now let's start more formally this Lyapunov stability theory. Now, what is important when you do control systems analysis and design is not to allow the mathematics to overcome you. So the mathematics should be a tool to formalize to some extent what the intuition tells you. So not the other way around. So don't blind yourselves. I'll give you an example. So once I went to the University of Michigan, and I was with my friend that was a researcher there, and there was an invited researcher, very famous, that published many books on control theory. And he had just published a book. Beautiful stuff. And he had only one example at the end, a simulation example, which was the classical problem of, I don't have, okay. You know this problem, you have a cart and you have a pendulum and you go from one place to a place and keep this upright. Okay. So yeah, that as an example. Hey, the trajectories were beautiful and stuff like that. So my friend asks him, look, what's the bandwidth of your control systems? What are you talking about? You know the bandwidth. So the bandwidth is what? If you give it a certain reference, which is to go to that point, then you have to evaluate the impact of your requirements for the force that you have to impact to do that kind of maneuver. And the bandwidth essentially tells you what's the highest frequency at which you should excite that system in order to do that beautiful maneuver. And in mechanical systems, typically you don't see bandwidths larger than 0.2, 0.3 radians per second, because you don't have actuators that can react to your commands above that. But because he was essentially a mathematician, he said, I don't care about the bandwidth, it's doing what I want it to do. Okay, let's compute the bandwidth. And the bandwidth was about 1,000 radians per second. So, I mean, you have to be very careful with these things, okay? There's no way he was going to be able to find an actuator to do that kind of motion. So be careful, the mathematics should go hand in hand with your physical intuition. It's very important. So Lyapunov introduced this concept of stability. And I'm going to say in words, And then the mumbo jumbo, it could be Tamil to me. I mean, it's equally complex down there. It will become very easy to interpret. He said the zero solution, the equilibrium point is stable if. So there's the equilibrium point. So think of this as a reactor working around a certain equilibrium point that through a coordinate transformation, I shift to zero. And I want to be able to initialize this reactor in a nice manner so that when it kicks in, it doesn't go completely bananas. So the question is, when do I call zero a stability point? He says, pay attention. The zero solution is stable if when I give the system a protective boundary, in other words, I want the system not to leave that boundary because it would be dangerous, then I can find another neighborhood such that if I start the system there, it will never leave the other boundary, the other protective boundary. So that's what we are seeing here, you see? It doesn't leave it. So boom, boom. So for every protective boundary or neighborhood epsilon, I can find a neighborhood delta such that if I start there, I don't leave the other one. That's stable. So mathematically, for every epsilon protective boundary, there is a delta that is a function of epsilon, such that if the trajectory starts inside a neighborhood of size delta, then the trajectory afterwards will not leave the boundary, the neighborhood of size epsilon. Okay, is that clear? So you are trying to protect yourself. I don't want to leave this because it would be chaotic. I want to start very smoothly. How can I be certain of this? That's stability. You may be a bit disappointed because you may say, well, it doesn't tell me that the trajectories go to the equilibrium point. But that's the first step. So that's stability. Okay. There's another concept that was introduced by Lyapunov, which has to do with the attractiveness. And forget about the word locally, it's not very important at this point. The zero solution, which is the equilibrium point, again, it doesn't have to be zero, but through a coordinate transformation, you may bring it to zero, is attractive if you can find a neighborhood such that when you start there, you go towards the origin. So mathematically, there exists alpha such that if I start my system inside the neighborhood of radius alpha, then the trajectories go to zero. Now you must say, oh, hold on your horse, what's going on here? This is what I want. Why should I care about stability, right? Because this is truly what you want. There are some strange cases where the system is attractive, but does funny things. It indeed converges to the origin, but goes to Pondicherry and comes back. And you don't want that to happen. So you want the two things at the same time, stability and attractiveness, okay? So it's very important. So the zero solution is locally, then I'll explain to you why we say locally, asymptotically stable if it is stable to prevent you from going to whatever, and attractive. That's the fundamental thing, okay? So one may have attractiveness, but not stability. So the two conditions are required. All right. There's a formal approach that I'm not going to insist upon it because you may read on your own. What is important are these basic concepts I gave to you, then I'm going to apply them to something interesting. For example, see the case of a stable system. This is, for example, the case, not exactly. If you have, I don't know, is there anyone from electrical engineering? If you have an oscillator, where you have with cursor around, it's stable, not asymptotically stable. This is unstable, and this is asymptotically stable. All right. So these are the definitions I mentioned to you, no problem. So there are at least 3 ways of assessing the stability, in the sense of stability plus attractiveness of a system. You solve the differential equation. This is total brute force. We don't want to do this. You linearize the dynamics around the equilibrium point, but then you may show that locally, if you don't start very far away, you are attracted to the origin, but God knows what's going to happen when you are far away. Or you use Lyapunov's direct method, which is elegant and powerful, and may yield global results. So this is the way I wanted to show you how this is written in most books. And you'll see that when you lift the veil of Maya, of all these things, it becomes clear. So they start by telling you that you have to consider this famous scalar function, candidate Lyapunov function, which is positive definite. And by this I mean it's always positive for all x different from 0, and it's equal to 0 for x equal to 0. You have another important word, which is positive semi-definite. That's why when instead of being greater than 0 is greater than or equal to 0. So this is also some nomenclature that people use. And then, of course, you may have negative definite or negative semi-definite if minus v is positive definite and positive semi-definiteness, okay? So that's it. And then the theorem goes as follows. This is in the form of theorem, because I want you to understand that when you study these systems, people can be very formal. That's not my usual approach. First, I go through examples, intuition, and then I build up the mathematics. But there's nothing to be scared about. So when you do these things mathematically, there are ways of writing. So let x be an equilibrium point for the system. We know what this means now. And suppose there exists a continuously differentiable function such that it is positive definite and the derivative is less than or equal to 0. This is not what I told you about. In those examples, I show that the derivative is less than 0. If the derivative is less than or equal to 0, the origin is stable. If the derivative is less than 0, which is the case that I showed you, then 0 is asymptotically stable. You have stability and attractiveness. So the bottom line is, when you wish to do something very interesting, then you have to concoct this Lyapunov function and make sure it is negative definite. Remember that here and there we use the word local. So local means that these things hold locally. In other words, when you have an equilibrium point, you can be certain that there is a neighborhood such that you start there, you get into the origin. Okay, but you'd like to be sucked to the origin when you start anywhere. That's called global. There's a technical condition that tells you that if the Lyapunov, I'm not going to show this, that the Lyapunov function is such that it looks like a big paraboloid. In other words, it blows up to infinity when you go away from the origin, then the origin, and now memorize this word, globally asymptotically stable. No matter where you start, you are driven to the origin asymptotically, okay? Now, okay, so I don't know how many of you will continue towards a PhD or writing of papers and stuff like that. But if you get into this business, you have to be very careful about the way you write things. I was blessed with my PhD advisor, Professor Pramod Khargonekar. He graduated from IIT Mumbai, and then he was my professor at the University of Minnesota, and he was a student of the famous Professor Kalman. and he used to tell me, António, the way to write a good paper is you write it, and then you read it, and when an equation arrives, you simply skip it, and what remains should sound like a mantra. So there should be beauty in it, okay? You have to learn how to do this, because otherwise nobody will read your paper. You can't be boring, and there has to be some elegance. So that's why sometimes people use this formalism. It sounds nice. You can, you know, the mathematical discourse now captures your intuition, and everyone is happy and satisfied. So I think I'll stop here. I have much more to show in what concerns Lyapunov, real examples. So I just want to ask you if you have any questions also from people that are online. Okay, let me see. How can I check this? No, chat room. Sir, I have one question. Yes, yes, go ahead, please. It's good he has questions all the time. Could you please comment on persistence of wow. I'm talking about apples and now you bring in oranges. Okay. How can I explain this? Okay, I'll give you a simple example. People first use the word persistent of excitation in the field of adaptive control theory. So in adaptive control, you have a model out there. You don't know exactly what the model is, what your plant does, and you try to identify it. So in order to identify the behavior of something or of a human being, you have to interact with that human being, right? So suppose you have a system. Okay, so suppose you want to characterize the characteristics of this wall from an acoustic standpoint. So you are here emitting waves, and if you are on the other side, and you want to see what the dynamic system is that consists of this wall, it is between the two of you, right? And it's more or less clear that it works as what we call a low-pass system. Low frequencies will get there very easily. As you pump up the frequency, then you hear less and less. So if you plot as a function of frequency, the ratio between the amplitude of the received wave and the emitted wave, it would be like something steady, and then it starts decreasing. So this particular corner has a specific name. So for example, if the wall has this corner at a very high frequency, then you could hear everything. If the corner is at a very low frequency, maybe you ask Ravi Shankar to play the sitar and you hear nothing on the other side, okay? So the question is, how do you actually find out about the characteristics of the wall? Well, you have to excite the wall. But you are not going to excite the wall just with low frequencies because you learn nothing. So you have to be persistently exciting. You have to be persistent, all right? And this term was somehow used in adaptive control because you have to guarantee that you are exciting your system so that you can understand what the system is doing, and then from that infer the behavior of the system. That's what we call, in a rough way, persistent of excitation. For the case of development of online learning, you mean machine learning? Okay, the answer is simple. I know nothing about machine learning. So, oh, a new message. Oh, yeah, that's what yeah. It's exactly in the context of a learning controller. So it's a form of adaptive controller. You have to have persistent of excitation. In other words, you cannot get into the situation where the plant does not get sufficiently excited, because then you are not going to learn anything about the plant, what the plant is doing. Is that okay? How do you prove our Lyapunov function? Oh, Yusen. Not just imagined by the person. Well, Yusen, it's what I told you. When you have an electromechanical system, more than likely a Lyapunov function that captures the physics of the system in terms of energy will work. When you are studying the evolution of competing species or a chemical reactor and stuff, I mean, what is the energy? So you have to imagine some Lyapunov function. So how do you imagine that? You do a bunch of things. You may have built up a menu of candidate Lyapunov functions for specific types of problems, and you just memorize them. Or you look at the equation and say, well, this equation is exactly the same type. It looks very much like the equations for an electromechanical system for which I can write the energy. So let me go ahead and write the energy function for an equivalent electromechanical system, except that I'm working with something completely different. And let's see what happens. Is that okay, Yusen? No, I know. Okay is not good enough. Okay, we'll talk some more later. Any other questions? Not now.
So we took one example where we talked about exact linearization, where we calculate.
You cancel nonlinear terms and stuff.
Yeah, so there you told we can't use that because we can't estimate alpha and beta.
And you may end up doing something completely foolish. You may think, well, I got rid of these fellows and they come back to haunt you.
Yes, sir. So using Lyapunov stability theorem that we just discussed, will that be helpful in calculating the control over there?
Yeah, because remember when I gave you this example where I didn't even know the shape of that function, k1 of x1, it's something vaguely in the first and third quadrant. So I don't know, I don't have to know specifically the parameters. As long as I have, at least in the case of mechanical systems, some properties that are physically sound, like they introduce a good damping or a restoring force, then I don't need to know the exact parameters. And that's the beauty of the thing. Yeah.
Sir, but where does the control come into picture here? Because till now what we did is we just looked if the equilibrium points are...
I skipped that part. Okay, so let's see here. With the model you present, is it possible? Okay, I'll get back to this. Yeah, that's an excellent question. So let me go back here. So I'm talking about 0, 0, 0. Where the heck is the freaking controller, right? Okay. In the most general setup, suppose you have a plant which is nonlinear. So dx dt is some nonlinear function of x and the input. Then what you measure is a function of the x. And somehow you want to close the loop through a controller that in this case, I'm assuming it's very simple, is u is a function of y. That could be a nonlinear function. This is a control problem now. Okay, so where is the 0? So when you write this, okay, maybe you are not used to this notation, dx dt equal to f of x and u. Okay, so let's go back. This is essentially that thing I mentioned to you before. You see, when I have two equations and I stack x1 on top of x2, And if I call this whole vector f of x, I say dx dt equal to f of x. But if I put some input here, u1 and u2, then this becomes a function of x and u. Okay, so that's where it comes from. All right. Okay, so I have a nonlinear plant that could be a ship. I'm trying to control something about zero, for example, the heading. This is described by a nonlinear equation. The input could be the rudder action. And then what you observe is actually the heading angle. Okay. And now this G satisfies this property, f of 0. These are technical conditions, not very important. And suppose you come up with a control law so that you read the heading and you set the rudder angle. And I have a very simple example, probably to not work for this case, where the rudder angle is a nonlinear function of heading. It's a weird controller, but anyway, we'll get there. When we put this together, what you get? Dx dt is equal to f. So you see there's a u there. So it's a function of x and u. But u is h of y and y is g of x. So you have f of x and now h of g of x. So now you have an equation where the u vanished. And the equilibrium point of this system is 0. So you are back to the original thing, an equation, there's no inputs because they were eaten in the process. Because when you close the loop, the inputs are a function of the output. And now you are back on the setting, a nice nonlinear differential equation, and 0 is the equilibrium point, okay? So that's how it appears. Now, here in India, do you address someone by the first or the last name? I always get confused. The first. So in this case, the first is Sivaraman. Yeah? No, Sivaraj is the last one. Huh? Shivaraman. Okay, yes. With the model you presented, is it possible for persistent of excitation condition? Well, the persistent of excitation condition has nothing to do with the model. You have a plant and you don't know exactly what the model is. You are trying to learn a model, so you have some strategy around it to excite this plant with sufficient excitation so that you understand how that plant is going to react. It's the same when you meet someone, when you meet people. I mean, if you meet someone and only ask a few questions, you are not going to know much about the behavior of that individual, right? And so if you want to know more, you ask all sorts of questions. And then sometimes when you ask too much, you have surprises. But anyway, that's what you have to do. You have to be persistently exciting, or, you know, about asking questions to that person to really understand how the person reacts. You are presenting cooperative system. I can think of a number of ways of answering your question here. Okay, let's think about cooperative systems. Yeah, but this doesn't have much to do with persistent excitation. I showed you a case yesterday where you have an underwater, call it a target or something, and you are trying to find out where the target is using a surface vessel, and you were measuring ranges. And the question is, can I possibly find, excuse me, can I possibly find where the target is just by measuring ranges? And remember, I told you the surface vehicle must be performing sufficiently exciting maneuvers, which is a very similar concept. So if the target goes along the straight line and the surface vehicle goes along a straight line, you'll not be able to find where the target is, because if you have the target going here, and if you have this vehicle going on the side, and if you measure ranges, the ranges that you get are exactly the same that you'd get if you were on the other side. So there's no way of distinguishing. So you have to get into the excitation, get to know what the target is doing. So yes, when you have cooperative systems, especially to track underwater things, you need this concept of persistent of excitation. Is that okay? Okay. So anything else? We'll continue tomorrow.
Sir, continuing with my question. So how to find that h, the function h?
The function h is you have to design it. So when you have a plant, you have to design a control law. How do you design that control law? You learn from your fellow, you seek divine inspiration, you do some computations, you come up with a control. Oh, I have a feeling this is going to work. Now let me analyze, and you do this. Okay.
Like in the linear case you told, like first write the desired thing that you want and then just compare the equations to get the control.
Oh no, that's not necessarily the case. When you have more complicated systems, you cannot just keep using that trick. No, you have to be more sophisticated.
So it changes case by case. We just can, we can't, means there is no general way of finding the control, but we can.
No, there are general ways. Okay. I mean, when you get into linear control systems, there's a class of systems for which, so you have this concept of the state, right? So suppose you have a mechanical system that you want to quench the vibrations to zero. So deep inside you have springs and dashpots and whatever, when they are all shaking. And the question is, how can you input some stuff so that everything goes smoothly to zero? So if you assume, for example, that you can observe all the guts of the system, in other words, you know what the springs are doing, the dashpots are doing and stuff, there's a concept which is to do state feedback. So the input is a combination of the states, all right? And then you have a beautiful theory of control that was initiated by Kalman, which is linear control theory. I'll probably talk about that a little bit. That gives you a very well understood way of doing the design, where you formulate the problem in a very abstract manner, but then the tools are out there, even when the system ends dimension 1000 or 2000 or 3000. So there are systematic methods of doing that. But so now you may ask, so what's the why? So why don't I start by teaching the general methods? And that's it. Let's get it over with. You'll never build up your intuition, because that's one thing. That's one thing that you learn. I mean, there are fantastic tools out there, but you shouldn't just download these tools from the net and play with this and there and see what happens. No, you have to have the intuition. The intuition should guide you. And you build the intuition by solving simple problems. They help you a lot. That's the important thing. So you have a problem you want to solve. You want to derive something to zero. You formulate the problem in a mathematical setup. There are many ways of solving that problem using fantastic design tools, but your intuition has to be there. Otherwise, I'll show you some cases, okay? All right. Okay, any other questions? Okay, so thank you very much for coming. I'll see you tomorrow. Okay, and bye-bye everyone out there. Okay, should we try that thing now? Thank you, thank you. We'll finish Lyapunov, and then I have to make a decision whether I'm going to cover a little bit of what he was just mentioning. And then after that, I'll be covering path following systems, and then I'll get into cooperative control. and then I'll get into navigation.
The navigation part, if you could maybe introduce a bit of measurements as I asked that day.
Okay.
Yeah, live often.